morning. So in the last part of our Chapter 12 discussion, we're going to talk about two basic topics. We're going to first work our way talking through the different types of the intermolecular forces and sort of how we can use those intermolecular forces to determine the relative boiling points of different materials. And then we're going to spend the last part of our discussion talking about solids specifically and categorizing solids into different categories. So let's start here with intermolecular forces. So we've already defined what they are and sort of some of the basic ideas behind them. And we mentioned that the stronger they are, the higher the boiling point will be. So materials that will have strong intermolecular forces, right, will tend to result in liquids and solids with higher boiling and also melting points. Whereas materials with relatively weak intermolecular forces will tend to either exist as gases if they're really weak, or low boiling or melting solids and liquids. So let's first look at what are the types of intermolecular forces. So there's three types of intermolecular forces that a pure substance can have. They can have what are called dispersion forces, dipole-dipole forces, and hydrogen bonds. And so we're going to go through each of these in a little more detail and talk about when they occur and sort of some different aspects of them. So let's start with dispersion forces. These are the most basic intermolecular forces in the sense that they occur in every single molecule out there has dispersion forces as a type of intermolecular forces. So these were first recognized in the early to middle 1900s by a scientist named London. So you might also hear these called London forces. And again, the key aspect of it is they're present in all molecules and atoms, right? So all materials have London forces or dispersion forces. Now, these are caused by fluctuations in the electron distribution within the molecules and atoms. Now, that sounds really sort of high level, and it can be if we delve really deeply into it, but we just want to understand the basics of why these occur and some of the different qualities or properties of molecules that can make them weaker or stronger. So fundamentally, these are the most basic intermolecular force, but they're probably also the hardest to sort of conceptually understand. So we'll just try to take this step by step and see if we can get just a basic understanding of what they are. Now, all atoms and molecules have electrons, right, in their orbitals that we talked about back in Chapter 9, right, around the atom. We have these electrons that exist in these areas of spaces that we call orbitals. And so since all atoms and molecules have orbitals and have electrons in them, they all have some type of dispersion or some quantity of dispersion force. Now, as we also talked about, these electrons are moving, right? They are not static, they are moving. And every so often, they become unevenly distributed, right? It's just a statistical phenomenon. They're moving around within the orbital spaces, and those orbital spaces are three-dimensional. And so every so often, they will become unevenly distributed on one side or the other of the atom. So visually, maybe we can think about it like this. So, maybe if we had the ability to take sort of instantaneous photos at different moments of the electrons, most of the time they would look something like 1 or 2 here, right? Where there's a relatively even distribution of, say, the 2 electrons in an orbital. Now for helium, say this is our 1s orbital, all right, it has 2 electrons in it, and these electrons are relatively even, distributed. But every so often, they group, right? They become unevenly distributed on one side or the other. And that creates what we call an instantaneous dipole, or sometimes called a temporary dipole, where one side of the atom or molecule has a relatively negative charge where the electrons are grouped, and the other side would have a relatively positive charge, right? That's a dipole. Remember we talked about polar bonds, right? Where we create a dipole where one side of the bond is more positive versus more negative, where the electrons spend more time. Same kind of idea here. Now, when this happens, right, it causes, if you will, a chain reaction. Right? So, with one atom or molecule gets this instantaneous dipole, it will induce instantaneous dipoles in the surrounding atoms, right? In 3 dimensions around it, right? And so if this is our starting molecule, if you will, and it had its electrons groups over here, it might cause the atom over here to create a dipole where the electrons are now repelled, right? Opposite charges or same charges repel each other. And so we get, the electrons move away from each other, so they would flee this way, creating an area of positive charge here and an area of negative charge over here, and you get this attraction, right? This positive negative attraction. This is your dispersion force here. And where you had the positive charge, right, that's going to maybe attract electrons from an opposite atom, again creating an instantaneous dipole over here, and again an area of attraction that we would think of as the dispersion forces. And this goes on in all directions, and of course once it happens here, then it's going to be induced in other atoms surrounding this one. So this is the idea of how these dispersion force gets created. Now, one thing to think about here, or just some ideas to think about, is that these are very short-lived, right? So, as I said, these fluctuations are occurring, right? So it's going to be here one instant, and then the next instant it'll be back to something like frame 1 or 2, and that particular temporary dipole will go away. But remember, we have millions of atoms here. And so, in every given time, some of these atoms are taking on these instantaneous dipoles and causing instantaneous dipoles in the atoms around it. So, while this one may go back to being like this, one atom over here might develop a dipole and cause it to spread out around it. So if you take all of this on average, you create, within the whole sample, you create these dispersion forces that will hold the atoms or molecules together. Now, how strong are these dispersion forces, right? Or what influences the strength of these? Well, it depends on how easily the electrons can form this instantaneous dipole, right? Or what we call polarize, right? Create a dipole. Now, this is related to the size of the electron cloud. Now, what's going to make the electron cloud bigger or smaller? Well, if there's more electrons, right, we have to have more orbitals, and those orbitals will become further and further away from the atom. That'll create a larger electron cloud. So, one way that we can think about it is molar mass, right? Now, molar mass is not the only factor, but molar mass will track with larger electron clouds, because as we add mass, we're adding more electrons. More electrons means electrons are going to be further away from the nucleus, creating bigger orbitals, or requiring bigger orbitals to hold them, which is going to create a bigger electron cloud. And again, the idea is that bigger electron clouds result in greater dispersion forces because they're easier to polarize. because those electrons are further away, easier to move around, right? They're easier to polarize. So the basic idea that we're going to use is as molar mass gets higher, we get more dispersion forces, or if you want to think about it, stronger dispersion forces. So we can look at a basic table here. This is just using a series of elements, in this case the noble gases, and just illustrating that as the mass goes up, the boiling point goes up. Now, remember, the boiling point is a way that we can look at the strength of intermolecular forces. So higher boiling point, of course, would indicate stronger intermolecular forces, or in this case, stronger dispersion forces. Okay, so those are dispersion forces. Now, the second type of intermolecular force that we'll look at is called the dipole-dipole force. Now, these don't exist in all molecules, unlike dispersion forces. They only exist in polar molecules. So, before we learned how to, in chapter 10, we learned how to predict whether a molecule is going to be polar or not. And we're going to use that idea to decide whether a molecule can have dipole-dipole forces, because if it's nonpolar, it can only have dispersion forces. If it's polar, it can also create dipole-dipole forces. Now, why? Well, because polar molecules have not just these instantaneous dipoles that are created when we have dispersion forces, we call them temporary dipoles, right? Polar molecules have permanent dipoles, right? They have a positive and negative part of the molecule. And so the fact that those dipoles are permanent means they can create those positive negative interactions between molecules, but they're not fleeting, right? They don't come and go as the electrons move around. They are permanent. And so what we see is the positive end, or the positive side of one permanent dipole in one molecule is attracted to the negative end, or the negative side of the permanent dipole in another molecule, and that creates what we know as the dipole-dipole force. Now, one thing we want to forget is that just because we have dipole-dipole doesn't mean we don't have dispersion forces, right? The dispersion forces are always there. But when we talk about molecules, we tend to only talk about the strongest type of intermolecular forces. And since these dipole-dipole forces are going to be stronger than dispersion forces in the same molecule because they're permanent, right? They don't come and go, then we tend to focus on those. So having these additional, stronger attractive forces will cause molecules that are polar to generally have higher melting and boiling points. Now, one thing to always keep in mind here is because dispersion forces depend on molar mass, then we have to make sure that when we start doing comparisons, that we try to compare molecules that have the similar molar mass. So in other words, we're sort of standardizing the level of dispersion forces. So if we're trying to decide which molecule is going to have stronger dipole-dipole forces, we want to compare molecules that have similar molar mass. Otherwise, we run into issues because if one molecule has a much higher molar mass, then it's going to could potentially have much stronger dispersion forces, which could actually make it have a higher boiling point, even though it has a lower molar mass, even though it has weaker dipole-dipole forces because of the dispersion force. So you just have to be careful, and we'll limit our comparisons to molecules that have similar molar masses. So if we want to illustrate this dipole again, and we'll take a sample molecule like CH2O, right, which has a dipole right, that runs along generally like this, where the oxygen has more of the electrons, right? The dipoles, the electrons are flowing this way. So we've got a relatively negative charge here, relatively positive. So when we have these molecules interacting, the negative side of one dipole will interact with the positive side of another dipole, creating your dipole force. So if we start to compare molecules and we take molecules of relatively similar molar mass and we look at one that is polar, formaldehyde, so therefore we'll have these additional dipole-dipole forces, and we look at a molecule that is nonpolar, which will only have dispersion forces. So they both have about the same dispersion forces because of the same molar mass, but formaldehyde has these additional dipole-dipole forces. So what we notice is an increase in the boiling point in roughly about a 70-degree increase in the boiling point, right? It goes from negative 88 up to negative 19. Now, we also notice an increase in the melting point, right? It goes from minus 172 to minus 92. So we see the effect here. So I want to take a brief moment here to remind ourselves, looking back at chapter 11, where we determined whether a molecule was polar or nonpolar. I want to look back at just a reminder of how we did that. So to determine whether a molecule is polar, you must answer two questions, right? You must determine whether the molecule has a polar bond. And remember, we're going to do that based on electronegativity difference. And so if that electronegativity difference is 0.5 to about 2, that's going to give me a, quote, polar bond, and that's one criteria. So the second criteria for having these polar bonds is, our polar molecule, is that we have a non-symmetric geometry. So just because we have polar bonds doesn't mean the molecule's polar. If the molecule is symmetrical, remember, those polar bonds will cancel each other out, creating what we consider a non-polar molecule. So we have to be able to have both of these factors. We have to have polar bonds, and we have to have a non-symmetric geometry. So if we look at a couple examples here, CO2, for example, it has a difference in electronegativity of 1, right? So it's polar, but it has a linear or symmetric geometry. So the molecule is overall non-polar. But on the other hand, something like CH2Cl2 has polar bonds, right? The CCl bonds, right, have a difference of 1.4, right? So we have some polar bonds. We also have a non-symmetric shape. So remember, and I use this example specifically because remember, this is a tetrahedral. And tetrahedrals would normally be symmetrical. But remember, if not all of the things around the tetrahedral or the trigonal planar or whatever it might be, even if it's a symmetric shape, if all of the atoms are not the same, then the dipoles won't be symmetric. And so you actually get a non-symmetric molecule. And because it's a non-symmetric molecule and has polar bonds, the molecule is polar. We could contrast that with something like methane, CH4, which has no polar bonds, right? And so since it doesn't meet the first criteria, no polar bonds, then the molecule itself is going to be nonpolar. So the bottom line is you have to go back to the Lewis structure, and you have to look at the electronegativities, and you have to be able to answer these two questions to determine whether a molecule is polar. And then once we know it's polar, then we know that it has the ability to have these dipole-dipole interactions. So the last type of intermolecular force that a pure material can have is what's called hydrogen bonding. And this is going to be relatively the strongest type of intermolecular force that we have. And it is present, again, in polar molecules, but only very specific polar molecules. So these polar molecules must have a hydrogen atom bonded directly to either a fluorine atom, an oxygen atom, or a nitrogen atom in order to exhibit these additional intermolecular forces, right? So sometimes we might just call these super dipole-dipole forces, or really strong dipole-dipole forces, because they are in fact the same force, but because of the hydrogen bond bonded to either a fluorine or oxygen or nitrogen, these forces can be even stronger. And so, for example, HF, ammonia, water, alcohols are another big one here, like ethanol and methanol. All of these molecules that have these OH, NH, or HF can exhibit these hydrogen bonding. So, why? What makes these super dipole-dipoles, or these hydrogen bonds, possible? Well, first of all, we have a really large or fairly large electronegativity difference. Remember, hydrogen is 2.1, and these are, three of the more high electronegative atoms. Okay, so that's one difference. The other difference has to do with the size, right? These are relatively small atoms, and so that means the molecules can get really close to one another, right? So fluorine, oxygen, and nitrogen are also among the smallest. So they're high electronegativity and small. So high electronegativity is not quite enough, right? Chlorine is high electronegativity, Cl, not all that different than oxygen, but it's much bigger than oxygen. And so the fact that these are small atoms, and so the molecules can get close to one another, is another factor that allows these extra strong dipole-dipole forces to occur. And you combine these two things, you get really strong dipole-dipole interactions that we now call hydrogen bonds because of the presence of that hydrogen bonded to the oxygen, nitrogen, or oxygen, fluorine, oxygen, or nitrogen. So we can illustrate this in something like CH3OH, right? So this is methanol, this is an alcohol, right? And we can see here in the alcohol the OH, right, there. So we have the OH, right? So we have that OH bond, which means that we can have hydrogen bonding. Again, but it's the same kind of interaction, right? The negative end of the dipole of one methanol molecule is interacting with the positive end of the dipole of another methanol molecule. And so we get this interaction that is just like a dipole-dipole, but just stronger. So it gets the name, these kinds of interactions get the special name of hydrogen bond. So, we can look at the effect these have. So, if you remember before, we compared these two molecules, right? Again, similar molar mass, and we saw an increase of approximately 70 degrees in terms of the melting point, right? So, ethane having only dispersion forces, right? Non-polar. Formaldehyde having additional dipole-dipole interactions caused the boiling point to go up by 70 degrees. So if we look at now methanol, right, which has a very similar molar mass, but instead of just having what we might consider normal dipole-dipole interactions, it has these extra strong hydrogen bonding interactions because of the OH here, we see the boiling point go up by essentially an additional, approximately 85 degrees or so. So a big increase here in the boiling point from negative 20 all the way up to 65 degrees. Right? Again, we also see, it's great. Now, one thing I will point out is the melting points don't necessarily change very much between regular dipole and hydrogen bonding. The fact that it can hydrogen bond doesn't have nearly the effect on the melting point that it does on the boiling point because of what's involved, what you have to do when you make that transition from a liquid to a gas, where you have to totally break all of those interactions, whereas in the melting, you only have to weaken them. So having those additional hydrogen bonds doesn't have such a dramatic effect all the time. Now, the other thing that becomes quite important here, right, is that in a lot of these cases, the presence of these hydrogen bonds will change what state that this material exists at under normal conditions. So ethane and formaldehyde both, right, are gases at normal temperatures, right? So if we think about room temperature at about 20 degrees, right, both of these are going to exist as gases. But having those hydrogen bonds makes the same size molecule exist as a liquid, right? A liquid with a pretty high boiling point, right? Above room temperature. And so the presence of this hydrogen bonding can have dramatic effects on, what the material or the properties of the material. Now, of course, we focus a lot on water because water is an abundant molecule. It's a molecule that is important for all sorts of aspects, right? And now we can even look at it again here because, of course, water has the ability to hydrogen bond because of the OH bond. And water is also a really small molecule. Now, why do I point this out? Well, notice, if we think about any other molecule that has a mass of only 18 or even much higher than 18, right, they all exist as gases. Right? But it is strictly the ability of water to hydrogen bond to have these strong intermolecular forces that give it such unusual boiling points, right, for the size of material, right? It boils at 100 degrees, right? 40 degrees, almost 40 degrees higher than what we just saw with methanol, which has a mass of 30. Now, because water is so small, and it has these hydrogen bonds become extremely strong, right? Because these molecules can get extremely close together and create very strong hydrogen bonds. And this has, dramatic effects on, everything that we do, right? This is the reason why water is a liquid at normal temperatures. And, goes into so many of the different things that we've talked about with water throughout the semester, right? Go back to the fact that it forms these strong hydrogen bonds. Now, one example, maybe the most important example, at least in terms of our existence, is the ability of the hydrogen bonds or the presence of hydrogen bonds in DNA. Right? So hydrogen bonds are what hold the double helix together in DNA, where you develop these 2 or 3 hydrogen bonds between the base pairs, right? You can see here that there's OHs on some of these, and they interact with the opposite side where there's a molecule that has electrons available, and so you can get that positive negative interaction where you're sticking these things together. But there's a balance here, right? So why was it important that hydrogen bonds are what hold the double helix together, right? So it's important because these are strong in one sense, and that allows DNA to be relatively stable. But they're not too strong. So one thing that we want to remind ourselves of is that while we talk about hydrogen bonds as strong, even hydrogen bonds are much, much weaker than, say, an actual covalent bond, right, that exists, between atoms in a molecule. Much, much weaker. So it's that balance between it being weak enough so that we can easily break it when it needs to break, right, when we want to unzip it, but it's strong enough so that it can hold together and be stable under normal cellular environments. So hydrogen bond, highly, very important in the function of a DNA molecule. Now, there is one additional intermolecular force that I want to mention. Now, this is not present in pure materials, right? This is a very specific type of interaction that is present when ionic compounds dissolve in water. So when we dissolve ionic compounds in water, right, because water is polar and forms these hydrogen bonds, right, what happens is when the ionic material dissolves, right, it forms its ions, right? It forms a positive ion and a negative ion. And these polar solvent molecules have a permanent dipole, right? So they have a positive side and a negative side of the molecule. And those dipoles can interact with the charged ion. So the negative ion can interact with the positive side of the dipole of the water molecules. The positive ion can interact with the negative side of that dipole. And you create what are called ion-dipole interactions. Now, these become extremely strong overall because each ion can develop multiples of these. So for, water, right, it means that with some ions it can form up to 6 interactions, or 6 hydrogen ion-dipole interactions with each ion. Right? And it's thought that this is one aspect of why ionic materials are so soluble in something like water and polar solvents, because the ions can be stabilized by these strong ion-dipole forces. Right? And these forces overall, right, would be considered stronger than hydrogen bonds on a scale, right? So, but remember, these are not going to occur in a pure material, right? These occur in a very specific type of interaction where we dissolve an ionic material into a polar solvent. Most notably, water is what we'll focus on. Okay, now we're going to shift gears here a bit and talk about our sort of last topic in the chapter, and that is looking at crystalline solids. And we're not going to really go into detail too much about solids here, but we're going to categorize them. And so if we think about crystalline solids, remember, crystalline is one type of solid, right? The other type is amorphous. And what makes a crystalline solid different is that it has a well-ordered pattern, right? It has a repeating pattern in the solid. So it's well-ordered, where amorphous has no long-range pattern. So we're going to focus on crystalline solids here. And so crystalline solids can be divided into 3 types. We have molecular solids, we have ionic solids, and we have atomic solids. And this is based on the individual units that compose the solid. So let's look at a chart. So we have molecular solids. These are going to be composed of molecules, right? So these are things like water, ammonia, right? Things that we know of as molecular solids. Remember, molecular solids are going to be made up of only nonmetals, right? We have ionic solids. If we remember, right, ionic solids are made up of metals and nonmetals, more specifically positive ions and negative ions. So the simplest unit is what we called, remember that formula unit, right? That simplest neutral unit of the ionic compound. So for example, table salt, that formula unit is sodium chloride. Right? So that's my individual units. And then atomic solids, these are going to be elemental solids, right? So these are the individual units are going to be individual atoms. So like gold is made up of a bunch of gold atoms. Now, the property that we're going to focus on here is melting point, right? And so if we have molecular solids, they tend to, as a class, have relatively low melting points, whereas ionic solids will tend to have high melting points. And atomic solids can be variable, and we'll get into more detail about that. So now that we've divided these into different types, let's look at maybe why we see low versus high melting points here. So first of all, molecular solids. Again, these are solids that are composed of individual molecules, like ice and carbon dioxide. They are held together, of course, by intermolecular forces, right? We saw water with its hydrogen bonds. Solid CO2 would be dispersion forces because it's a nonpolar molecule. But they're going to be held together by one of those three types of intermolecular forces that we've talked about. Or, in other words, it's going to have dispersion forces and may or may not have dipole-dipole or hydrogen bonds, depending on whether it's polar and whether it meets the criteria for hydrogen bonding. So we talked about the hydrogen bonds in ice, whereas dry ice is only dispersion. And we notice, of course, ice melts at a much higher temperature, 0 degrees, versus dry ice, which doesn't melt, it sublimes, but a similar transition, but at a much lower temperature, minus 78 degrees. So bottom line is what that's telling me is that because ice melts at a much higher temperature, it has a much stronger type of intermolecular force than CO2 does. So, but even as a whole, right, even these, really strong hydrogen bonding with strong dispersion force, intermolecular forces, still have relatively low melting points, right, 0 degrees. So molecular solids as a whole have low, maybe to moderate low melting points. And it goes back to the fact that they're held together by intermolecular forces. Now, if we turn our attention to ionic solids, right, so remember ionic solids exist in these crystal lattices composed of positive and negative ions. And if we remember, those ions are held together by ionic bonds. So notice not intermolecular forces, but ionic bonds. And of course, any kind of bond, whether it be ionic bond or covalent bond, are going to be much, much stronger than any type of intermolecular forces. And so because these ions are held together by much stronger interactions, it's going to take much more energy to break those ionic bonds than it would the intermolecular forces, and therefore these ionic molecules, ionic solids, will have much higher melting points than molecular solids. So for comparison, while ice melts at 0 degrees, sodium chloride melts at 800 degrees. So these have really high melting points. Now, lastly, we turn our attention to atomic solids. These are solids whose individual units are individual atoms, like diamond, where we have carbon, or iron metal, or noble gases like xenon, when they can be put into a solid at really low temperatures, right? These are examples of atomic solids. Now, atomic solids can be held together by different types of interactions depending on the type of atomic solids they are, and this is why they have variable melting points. So we have 3 different types of atomic solids. We have covalent atomic solids, we have non-bonding atomic solids, and we have metallic atomic solids, each held together by a different kind of interaction. So let's look at a chart again and divide these three to look at these differences here. So at first, we look at covalent atomic solids. So these are going to be held together by covalent bonds. So an example of this would be silicon or carbon, so graphite or diamond. These are going to be examples of covalent atomic solids. And these are going to have, again, high melting points because they're held together by a bond, right? Non-bonding atomic solids, these are going to be held together by an intermolecular force, specifically dispersion forces, because these are elements, right? So they're going to be non-polar, and so these will tend to have relatively low melting points because they're held together by these relatively weak dispersion forces. Now, metallic solids are held together by a different kind of interaction, one that we don't really talk about in this book, and those are called metallic bonds. And again, metallic bonds can vary in strength depending on the metal. So what you end up with is metals have melting points all over the place. So let's turn our attention to these covalent atomic solids. So the classic example, or the most well-known example here, is diamond, right? So covalent atomic solids are held together by covalent bonds. So just like we saw with an ionic solid before, right, they're held together by bonds, in this case covalent bonds. And if you look at the structure of diamond, each carbon atom is covalently bonded to 4 other carbon atoms in a tetrahedron shape. So this makes this a very rigid, very hard to break down solid, right? You'd have to break some of these covalent bonds to get this to melt, right? These are going to be really difficult to do. And so these bonds are very strong. And so if we're talking about covalent atomic solids, will tend to have really high melting points. Diamond, for example, has melting points right around 3,800 degrees. So even much higher than an ionic solid like sodium chloride. Covalent atomic solids have extremely high melting points. Now, non-bonding atomic solids, as we said, they're held together by dispersion forces, which is going to result in them having relatively weak interactions, and therefore they should have really low melting points. So xenon was one example that we gave for these non-bonding solids, or when they're in the solid form, they're held together by simply intermolecular forces. So xenon, like other non-bonding atomic solids, have really low melting points, again, well below 0. Right? So this would be not a lot different than what we saw with molecular solids, where they're held together by intermolecular forces, but some of those can be held together by stronger intermolecular forces, like water, for example, so they have much higher, melting points, maybe 0, but, things like dry ice, molecular, it's a molecular solid because it's a molecule, but it's still held together by dispersion forces. So again, we saw a very low, in that case, sublimation point, minus 78. Xenon, a little bit lower with those dispersion forces, and minus 112. But the bottom line is relatively low melting points for these non-bonding atomic solids. And then again, lastly, metallic atomic solids. These are going to vary depending on the metal. Again, these are held together by what are called metallic bonds, which, again, we don't get into. You can know that they're held together by something called metallic bonds. And they have varying strength depending on the metal. So, for example, you have something like mercury that has a low melting point, exists as a liquid at room temperature, so minus 39 Celsius. where you get other metals such as iron that have relatively high melting points of 1800 degrees. And there's some metals out there that melt well above that, maybe 2,000-3,000 degrees. Right? And so melting points of metal all over the place, right? And there's ones that are in the middle. So you've probably seen things like aluminum, and these other metals will melt, if you put them in a relatively hot flame or a fire, right? Like gold. These things will have melting points that are, somewhere in between theirs. The bottom line is metals will vary because of the varying strength of these metallic bonds. So to close out this chapter, I want to make just a couple points here, and that is to focus a little bit on water. So this material is in the book. I didn't put it in the study guide, but I just want to make some points about why water is such an important molecule and we focus on it so much. Part of it is because it's so unusual. And again, the reason I'm talking about it here is because most of that unusualness stems from the fact that it can make very strong hydrogen bonds. So the bottom line is life is impossible without water. Now, because of these hydrogen bonds, a water molecule which has an extremely low mass, 18 grams per mole, exists as a liquid instead of a gas. Right? Imagine if not for these hydrogen bonds, all the water that we know would exist as a gas, and life would not be possible in the form that it is. And so the fact that water even exists as a liquid under normal atmospheric conditions that we know is due to the presence of these hydrogen bonds. Now, it also gives it a high boiling point, right? So because of this, right, we saw that it has a high boiling point here. It also has, a bent geometry, right? The bent geometry is part of the reason why it can have these hydrogen bonds, because it's very polar, right? So we have this very polar molecule, which means that has an OH, which means that it can have these very strong hydrogen bonds, which allows it to have a very high boiling point, which means it exists as a liquid instead of a gas, again, allowing life to exist the way that it does. Now, because of its high polarity, right, it also allows it to be a very good solvent. Right? So it dissolves ionic materials very well. It, of course, dissolves other polar materials, right? We talked about like dissolves like in a previous chapter. And it's even a reasonable solvent for some molecular compounds. As a result, right, water, right, often called the universal solvent, is the main solvent of living organisms. Right? So we've evolved to be water-based creatures, right? Carbon-based. But, water is the solvent that our bodies use and all living organisms use for transporting things around the organisms. Now, that's one thing, right? But what are some other things that this high polarity, high ability to hydrogen bond, what other things does it cause? Well, it also sets up a weird or unique way of freezing, right? Because of the shape of water, it freezes, and when it freezes, the water actually expands. So ice is less dense than the liquid version, which is extremely unusual, right? So because it expands when it freezes, it's less dense, and then it floats, right? So we get ice floating on top of water, right? Which is unheard of, right? In other materials, right? If a part of a material starts to form to a solid, it would instantly sink to the bottom. Now, this is, of course, extremely important because, right, that means that whether it's in the Arctic Ocean or in our neighborhood pond, that floating ice provides a layer of insulation which allows organisms to live in that water all throughout the year, survive the winter, right? If all of that ice were to sink, it would crush the living organisms. It would, essentially wipe out life within that every time it froze, right? And you wouldn't have the same kind of ecosystems as we have with ice being able to float on the water. So the fact that it has the ability or freezes in this unique way because of its, small nature, its geometry and polarity is another sort of remarkable idea about water. And lastly, when water freezes, we just said it expands, and this is why we can't allow our cells to freeze, right? If a cell freezes, the water expands, it will burst the cell, and so living organisms cannot survive freezing. So either we have to have ways to regulate our temperature, okay, or we have to be in a warm environment. So, that expansion, right, is not such a good way, right? Fruits and vegetables don't freeze very well unless we take precautions and we do what's called flash freezing so that the water molecules can't expand, right? They don't freeze in the same way, and so they don't burst the tissue, and so you can thaw them out, and those fruits and vegetables still maintain some of their integrity, right? If you were to allow it to freeze fully, imagine if you've ever had lettuce get too cold, right, and it freezes, and then if it unthaws, it just turns into this ick, very soft, without any structure, because you've basically burst all of the cells, and now you just have this sort of gelatinous goo. So, bottom line is water is an essential and quite a remarkable molecule and an unusual molecule. So while we focus on water a lot and its sort of unusual nature, we have to understand that it's an outlier, right? It doesn't follow a lot of the trends, a lot of the basic ideas that most other molecules follow. That's important in a lot of ways, but it also is a little bit of a caution that we need to sort of treat water as a little bit special and not sort of lump it in with all the other molecules because of its sort of unique properties.